Hello. Cycloadditions occur when two molecules combine to form a cyclic system. Let's consider different types of cycloadditions to see what might drive them. Carbenes are relatively unstable 6-electron species. They add to alkenes to form cyclopropanes. The driving force is clear. In the cyclopropane product, the carbon that only had 6 electrons now has 8. Incidentally, cycloadditions are named according to the number of atoms in each component that combine to form the ring. In this case, it's 1 plus 2 or 2 plus 1. Doesn't really matter. Epoxidation of alkenes is a reaction I've covered previously in my epoxides video. I will leave the link below in case you haven't seen it. The driving force for this reaction is exchange of a weak oxygen-oxygen single bond for two more stable CO single bonds, even though they're in a strained three-membered ring. This 3+2 cycloaddition was behind the 2022 Chemistry Nobel Prizes. Organic azides heated with alkynes can cycloadd in two ways. Head-to-head to give 1,5-triazoles, and head-to-tail to give 1,4-triazoles. These are regioisomers, and a reaction that gives more of one than the other is regioselective. Only the 1,4 regioisomer is formed when copper is added as a catalyst to this reaction. It becomes 100% regioselective. More on regioselectivity is described in my book and video on epoxides. Ozone is like organic azides. There's no way to describe it without drawing charges. It adds to alkenes in another 2+3 cycloaddition. Curly arrows show the driving force for this reaction. Production of a molecule where every ring atom is neutral from a charge-separated intermediate. However, the product is unstable. It decomposes via retro 2+3 cycloaddition to give a carbonyl oxide and a carbonyl compound, in this case, methanal. Reduction of the carbonyl oxide with dimethyl sulfide gives another carbonyl molecule and dimethyl sulfoxide, DMSO. Osmium tetroxide is a strong oxidizing agent. It cycloadds to alkenes via a 3+2 process. Addition of osmium tetroxide involves reduction of the osmium from +8 to +6 oxidation state. That is the driving force. Hydrolyses of these cycloadducts give 1,2-diols. That is called dihydroxylation. The poster child for cycloadditions is 4+2 of dienes with alkenes. Reasoning why this occurs earned another set of Nobel Prizes. Now we have to use molecular orbital theory. The 4 diene p orbitals can combine with their signs completely in phase, or with one more node, 2 or 3 more. This reminds me of plucking guitar strings. One string may vibrate with a long wavelength, low frequency, lower energy, but another may vibrate with twice the frequency, shorter wavelength, higher energy, and so on. Each p orbital contributes 1 electron to the pi system, so there are a total of 4 to place. When these electrons are added bottom up to the molecular orbitals created, the second one becomes the highest occupied molecular orbital, HOMO, and the third one is the lowest unoccupied molecular orbital, LUMO. Now let's look at the alkene pi orbitals. There are 2 p orbitals, each with 1 electron. When these are combined, both the electrons go into the lowest molecular orbital created. So that's the HOMO. And the other one becomes the LUMO. Molecular orbital descriptions of 4 plus 2 cycloadditions are based on what happens when the HOMO of one component, that's the diene here, overlaps with the LUMO of another, the alkene. 2 molecular orbitals are produced, and the 2 electrons that were in the HOMO of the diene are now in the lowest of them. Voila, we have stabilization. If there is an electron withdrawing group on the alkene, both its HOMO and its LUMO will go down in energy. Then when the 2 components cycloadd, more energy is liberated. Alkenes with electron withdrawing groups are therefore excellent dienophiles in this 4 plus 2 cycloaddition reaction. The first reaction I ever did in a research lab is a classic 4 plus 2 cycloaddition between furan and maleic anhydride. I simply mix these 2 components neat, and hours later, a single product crystallizes out. This has the maleic anhydride fragment extended from the furan part and these 2 hydrogens shown underneath. This one is called EXO. Here is a challenge. Can you draw the endo product? Cheerio, and thanks for watching. Bye-bye.